Okay, guys. Today we are halfway through our unit on optimality and duality. So we're going to talk about the KKT conditions today. Last time, to give you a reminder of what we talked about on Wednesday, we talked about duality in a kind of general way. We looked at problems that were of this form: generic optimization problems. Criterion is F. We have inequality constraints hi of x less than or equal to 0, and equality constraints Lj of x equal to 0. And we defined this object called the Lagrangian. And the Lagrangian was a function of our primal variable x from this optimization problem, and also a function of what we call dual variables, u and v. And so we had one component of u, let's say, per inequality constraint, and one component of v per equality constraint. And we restricted our attention to u's that were non-negative in every component. And we constructed this function called the Lagrangian, which is given by taking the criterion, adding ui times hi for each one of the inequality constraints, summing it up, adding vj times lj for each one of the equality constraints, and summing that up. Okay, so it's again a function of x, u, and v, where x is our primal variable and u and v are our dual variables. And we defined this thing called the Lagrange dual function, which was given out by minimizing over x. So we take an unconstrained minimum over all x, and that gives us a function of u and v alone. Those, like I said, we call dual variables. Sometimes we call them Lagrange multipliers. And this thing we called g. And the dual problem that we defined was to maximize this Lagrange dual function over all vectors u that are non-negative, component-wise. And even though this looks simple, as we saw in the case of LPs, in the case of QPs, it's going to be commonly the case that this g actually has implicit constraints as part of its domain. So in the case of LPs, this g is going to be a linear function, but subject to a bunch of linear equality constraints. So we define it to be, let's say, negative infinity when those constraints don't hold, which means that actually we have effectively more than just this non-negativity constraint on u. Okay, so the dual problem itself can have rich constraints. They're just hiding in the notation we have for the dual function here. Okay, it's going to be negative infinity outside of its domain. Okay, but if you recall from last time, this construction was performed in such a way that the maximum of this problem, which is called the dual, g star, is always smaller than or equal to the minimum value here, the optimal value in this problem, which is called f star. So we constructed this problem so that it gave us a lower bound on the optimal value to our original problem. That's called weak duality. That is true by virtue of our construction. There are no conditions under which, there are no conditions that we need in order for that to hold. That's just always true. Another thing that's always true is that this dual problem is always a convex optimization problem, or more specifically, it's always a concave maximization problem. Okay, that was true again just by the fact that we could have thought of this as a negative pointwise max of a bunch of functions, and those functions as functions of u and v were all linear. Okay, so that was, and then we used an operation that preserved convexity rule. Pointwise max preserves convexity. We viewed this as a negative pointwise max of a bunch of linear functions, which are convex, and so it was itself concave, right? The negative of a convex function. So those are two very general properties. And at the end, then I told you about this, an example of what's called constraint qualification. This is a particular form of that called Slater's condition, which is, these are conditions under which we get strong duality, that actually in constructing this dual, we get an optimal value g star that's exactly equal to f star. And one of those conditions, the one we learned, which is a simple constraint qualification condition, is called Slater's condition. If the problem in the primal was convex, so if this problem was convex, and there was a point that satisfied the inequality constraints strictly, so there had to just exist some value of x for which hi of x is strictly less than 0 for all I, then we get strong duality. Okay, geometrically this says something like the relative interior of the constraint set has to be non-empty. Okay, the constraint set can't be kind of pathological in that sense. And there was an even weaker form of that, which was that if a bunch of these were affine functions, we only needed this to hold for the non-affine inequality constraints. Okay, so in particular, if all we have are affine inequality constraints, then there are no conditions required for Slater's condition to hold, right? It just holds automatically if the problem is convex. So we're going to see today why strong duality is so important. We're going to see what the implications of that are. Has a lot of implications for how we understand the optimum solutions of problems. Let me pause for questions before I go into the KKT conditions. No questions about duality? Okay. So today we'll talk about the KKT conditions, give lots of examples, and then we're going to talk about two applications of the KKT conditions. One is to prove something that you guys have seen pop up in, very often, let's say in statistics or machine learning literature, where we claim an equivalence between constrained versus a penalized or Lagrange form. We can think about regularizing as a constraint or as a penalty. We're actually going to prove that those are equivalent. And the last thing, which I hope to have time to get to, because it's not that complicated, and I think it's an interesting conclusion, is we can use the KKT conditions to prove that for a very general class of problems that have L1 penalties, we get a unique solution as long as the data are sufficiently random. Okay, so it's an interesting example of uniqueness without strict convexity. So let's just start with the KKT conditions. We're going to have this general problem form like we did with duality. For the moment, we're not going to be requiring convexity, though I think you're going to see our strongest conclusion is going to be involving a convex problem. But in general, we can define a set of conditions. There's 4 conditions to be precise that we call the Karush-Kuhn-Tucker conditions, or the KKT conditions for short. And these conditions are as follows. So these are conditions that involve x, a primal variable, and dual variables u and v, just like we would in defining a Lagrangian. And the conditions are as follows. The first is called the stationarity condition, which says that if we take the Lagrangian, okay, and we take a sub gradient of the Lagrangian with respect to x, so maybe I should have written an x, just to be clear. This is a sub gradient with respect to x of the Lagrangian function. This has to contain 0. That's called stationarity. The second condition is called complementary slackness. It means if we look at all of our dual variables and all of our inequality constraint functions, okay, then either one or both have to be equal to 0 for all I. So the product of ui times hi of x must be equal to 0 for all I. Remember, our dual variables are constrained to be non-negative. These inequality constraint functions are constrained to be non-positive. Okay, and this is saying that at least one of ui or hi of x has to be equal to 0 for all I. And the last two conditions are called primal feasibility and dual feasibility. They're just very straightforward. The x that we're looking at has to satisfy the primal constraints, and the dual variables we're looking at has to satisfy the dual constraints. Well, that's just saying that u has to be bigger than or equal to 0 in all components. Okay, so we're going to think of these as a set of conditions, again, on x and uv. And what we're going to be doing in the next several slides is proving that in a very general sense, these are necessary and sufficient for optimality. So if I had an x and a uv that satisfy these 4 conditions, then x is primal optimal and u and v are dual optimal. Okay, it's not always the case, but it's the case for a large fraction of problems, especially convex ones. Okay. Right. So let's start with necessity. This direction is fairly straightforward. So let's suppose that I gave you solutions x star and u and v star. And I told you they were primal and dual solutions. And I told you one more thing. I actually told you that not only are they solutions, there's zero duality gap. So the value attained by u and v is equal to the value attained by x with respect to their own problems. Right? F star is equal to g star. That's the premise for this. So in that case, okay, we can derive a sequence of inequalities that's going to be very informative. And it's a very simple argument. Well, we know this is true. This is true by assumption that f star is equal to g star. But remember, by definition, okay, g was equal to the minimum of the Lagrangian over all x evaluated at its argument. So here, u star v star. Right? So this is just writing out the definition of g. This is equal to the minimum over all x of f of x plus the sum of u star I hi plus the sum of v star j lj. And, okay, well, certainly the minimum is less than or equal to the value of the Lagrangian at any one point. Right? So let's just pick the point where x is equal to x star. Okay, so this is certainly true because the minimum, again, is smaller than the value achieved at any one point, let's say at x star in particular. So we can upper bound this by the value of the Lagrangian at x star. And lastly, okay, because of the fact that x and uv were feasible for their own problems, this thing is going to be less than or equal to 0 for all I. That's going to be bigger than or equal to 0 for all I. So this whole term is less than or equal to 0. And this term is equal to 0, right? Because these are equal to 0 for all j. So everything we've added here to f of x star is less than or equal to 0. That's just by feasibility. So we can say this is less than or equal to f star. Okay, so again, this is super simple sequence of equalities and inequalities. This is by assumption. This is by definition of the dual function. This is just plugging in one value of the Lagrangian and claiming it's bigger than the minimum. And this is just using feasibility. And look, we've ended up with, on both sides, f of x star. What that tells us in particular is that all of these inequalities are equalities. So the inequalities that we saw here are both equalities because we've sandwiched a bunch of inequalities between two things that are equal. Okay, so we're going to look at actually this inequality and this equality, and we're going to read off in particular the implications of that. Let's look at this first inequality. So this first inequality we can write as min over all x of Lx u star v star is equal to L of x star u star v star. Right? That was an inequality that we knew was now an equality. And what this tells us is that x star minimizes the Lagrangian fixing u star and v star over all x. That's exactly what that tells you. And we know that actually this is equivalent by subgradient optimality it's exactly equivalent by subgradient optimality to actually this statement. If we just put stars and everything, right? It's just, this is a function now, let's say, of x. Think of u star and v star as fixed. If it's minimized at x star, we know that that's completely equivalent by subgradient optimality to a subgradient of this containing 0. And that's exactly stationarity. Okay, so we've seen that actually, we've just shown that the stationarity condition must hold, right? Stationarity condition must hold. That was just because this must be an equality. That implies stationarity condition. That was just subgradient optimality. Okay, let's look at this next one. This inequality here. This being an equality, okay, in fact tells us that, well, this is 0, right? It tells us that this thing must be equal to 0. Not just less than or equal to 0, but actually every term here has the same sign because that's less than or equal to 0 and that's bigger than or equal to 0. So if they sum to 0, each one of these has to individually be 0. Right? We can't get any cancellation because all the terms have the same sign. So the sum being 0 implies every term is 0. And that's exactly complementary slackness. Right? ui times hi of x is equal to 0 for all I. So just to recap, we've just shown that if x and uv are primal and dual solutions, and they have 0 duality gap, then we've shown that the stationarity condition must hold, complementary slackness must hold, and of course they must be feasible because they were solutions. So we've just shown that the K and D conditions must hold. Okay, so this is the one direction. We call this necessity. If we have solutions under strong duality, we must have the KKT conditions. And let's just note that nothing we've said here assumes anything about convexity, a priori. We haven't used convexity at all. We've only assumed that we had solutions that had 0 duality gap. Okay, doing the other direction. The other direction I would say is probably even more straightforward. Okay, let's suppose we have a triplet that satisfy the KKT conditions. Satisfy that set of 4 conditions. Then by stationarity, okay, we're just reversing this implication. Stationarity is this statement. Okay, by subgradient optimality, we know that that means that the Lagrangian, let's say fixing u star and v star where they are, is minimized at x star. Okay, so that exactly means that the dual function, which is the minimum of the Lagrangian, is equal to the Lagrangian at x star. That's the statement. And now we're going to use feasibility to say this is 0. Right? That's one of the 4 conditions. And we're going to use complementary slackness to say that this is also equal to 0. So this whole thing, right? If x, u, and v satisfy the KKT conditions, this whole thing is equal to f of x star. And what we've shown then is that the duality gap is 0 at x and uv, and that means that we have the solutions. Right? By construction, GUV is a lower bound on f over all feasible points. So if we ever have an x star that achieves the lower bound, then it is optimal. And the same is true from the dual perspective. F is an upper bound on the dual criterion value, and if we have any u and v that achieve that upper bound, they must be optimal. Okay, so 0 duality gap, as we said at the end of last week's lecture, implies optimality. So what we've shown, to recap, is that if we have a triplet that satisfies the KKT conditions, then they are primal and dual solutions. There are no caveats. That's always true. So to recap, this is what we just shown. The KKT conditions are always sufficient. So if you can verify that they hold, you have a solution. In fact, you have both primal and dual solutions. And they're necessary under strong duality. So if you're looking at a primal problem that has a dual that's tight, so we have strong duality, then they'll be necessary as well. So sometimes, I think this is the most accurate summary of the KKT conditions. But sometimes you might be thinking about convex problems in particular, of course, for the most part in this class. And so you might think of something like, if you have a primal problem that has strong duality, for example, if a primal problem is convex, and there are feasible points that satisfy the inequality strictly, so Slater's condition holds, then you know that you have strong duality in that primal problem. And then the KKT conditions are necessary and sufficient for optimality. So they're satisfied if and only if you have the a primal and dual solution. Okay, there's a bunch of really simple arguments, but it could be a lot to take in. So let me pause for questions. Okay, so a warning that I'll make about the stationarity condition. Okay, the stationarity condition, you might see this written in different ways in different texts. So the Boyd and Vandenberg text describes the KKT conditions differently than what we're doing in this class. But that book actually doesn't have subgradients at all, so it's going to have to be different because they don't even consider subgradients. But just a warning about the subgradient, about the stationarity condition. You will sometimes see this written in terms of gradients rather than subgradients when the criterion is smooth. Okay, but that's not going to be equal to the subgradient necessarily unless the function is convex. Right? We saw several simple examples of functions that were non-convex and smooth, but didn't have subgradients. Like, for example, x cubed has a derivative at 0, but it doesn't have a subgradient at 0. So what I mean to say is you cannot replace this with a gradient unless this whole thing is convex in x. Then it's not an equivalent condition anymore. Okay? You might see some people define things a bit differently, and therefore the KKT conditions might be phrased a bit differently. But that was just a warning about the non-convex case. Okay. Yeah, and just to emphasize, I guess, that, again, these were very simple proofs, right? So simple that you can easily kind of forget what's happening in each step. It's just so easy, it's hard kind of thing. But it has very deep implications, just like duality. Now we have a set of conditions that's, for a lot of problems that we care about, necessary and sufficient for optimality. So just a historical note for fun, before we give examples. Some people who took optimization, let's say 20 years ago, would know these as the Kuhn-Tucker conditions, not as the Karush-Kuhn-Tucker conditions. So Kuhn and Tucker were both giants in convex analysis. They're very famous. And in fact, I don't remember which one of them, but one of them was Rockefeller's advisor. So Rockefeller wrote the book on convex analysis. One of these two was his advisor. I can't remember which one. And if you look at, for example, the Rockefeller book or other older treatments on optimization, these would be called the Kuhn-Tucker conditions after some work by Kuhn and Tucker in 1951. But it wasn't until later that people found out that, much, much later, I mean, I think this is now the 90s, that people found out that there was a master's student named Karush who had the same conditions in an unpublished master's thesis in 1939. So he actually had these conditions a bunch earlier. And now we call them the Karush-Kuhn conditions, and we put his name at the very front, I guess, to acknowledge the fact that he had them so much earlier. So now they're the KKT conditions. Another note is that for unconstrained problems, so if my primal problem had no constraints, okay, if there are no inequality constraints, no equality constraints, then these are vacuous, right? In fact, I have no dual variables because I have no constraints, so these are vacuous. And this is exactly subgradient optimality, right? These sums don't appear because they're empty. I have no constraints. And this is just saying that 0 must be in the subgradient of f at the point x, which we already know is necessary and sufficient for optimality, right? If I'm just minimizing one function. So the Karush-Kuhn-Tucker conditions are a generalization of subgradient optimality for constrained problems. That's one way to think about them. And they reduce to subgradient optimality without constraints. So a lot of times you might hear people talk about the KKT conditions for unconstrained problems, and they just do it out of habit. That they're just referring to subgradient optimality, taking a subgradient in the criterion and setting it equal to 0. And one other note is that it turns out that if we looked at general convex problems and we wrote any constrained problem as an unconstrained problem, right? We did this trick that we've done before, which is we say that minimizing f of x subject to a bunch of hi's less than or equal to 0, a bunch of lj's equal to 0. This is equivalent to minimizing f of x plus the sum of indicators, right, that the constraints hold. Right, these problems are equivalent. This one does not have constraints. Now I can take a subgradient of this criterion with respect to x, set it equal to 0, and that is a necessary and sufficient condition for optimality. that in fact looks like this. Right? If all these functions are convex and the LJs are affine, let's say, then I can distribute the subgradient through the sum. So I have the subgradient of f plus the sum of subgradients of the HIs. But remember, we saw that the subgradient of the indicator function of a set is the normal cone of that set. That's what I'm denoting right here. This is the normal cone of the set of all x for which HI is less than or equal to 0 at a point x star. And this is the normal cone for these equality constraints. And this is actually equivalent to the KKT conditions. So this is an alternative construction for the KKT conditions. It's, I think, much harder to view things this way. But for those who are interested in convex geometry or who want to read about this, we could also have arrived at the KKT conditions through this kind of argument. It's just not necessarily, I think, as clear. Okay, so let's get to some examples now. The first example we're going to see is how to minimize a quadratic subject to equality constraints. And in particular, we'll look at the equality constraint that a times x is equal to 0 when we're minimizing the quadratic 1/2 x transpose qx plus c transpose x. Okay, and some motivation for why we're studying this. Well, we'll learn Newton's method in the next algorithms unit, so that's going to be a couple lectures from now. And we'll see that when we have equality constraints, we're going to actually take a Newton step to try to respect those equality constraints. And we'll be solving inner problems in Newton's method that are exactly of this form. Minimize some quadratic subject to an equality constraint. So you'll see that pop up very soon. So let's just brush off the rust and remind ourselves what the minimizer is without constraints. Hopefully, if we do this enough times, you guys it'll become like second nature. So what's the minimizer of this problem without constraints? Or how do I solve this without constraints? This problem. Let's say Q is PSD. Okay, Q is strictly positive definite. So I take the gradient, set it equal to 0, right? So Qx equals C. Is the gradient equal to 0? So x is Q inverse C. Minus Q inverse C. But I guess what we can think about is, oops, I'm sorry, I didn't show you half of the. So that's the reason why you guys couldn't say it. It's my fault. This Qx equals C is like a linear system of equations that we have to solve to get the solution, just by setting the gradient equal to 0. Okay, that was the unconstrained case. Let's do it with constraints now. With constraints, we're going to use the KKT conditions. Okay, so let's first write the Lagrangian. So we don't have any, did I use a U or a V? I used a U. We don't have any inequality constraints, right? We only have equality constraints. The Lagrangian is the criterion plus the sum of, let's say, ui times the components of this inequality constraint. And I can write that as plus, let's say, u transpose ax. All right, I'm just summing up ui times, if A has rows ai transpose x. Okay, so the KKT conditions are stationarity, the first one, which is just saying that if I take a subgradient Lagrangian and with respect to x and set it equal to 0, that's stationarity. But this is convex, right? I told you that, let's say, Q is positive definite. This is convex. So stationarity actually becomes that the gradient of the Lagrangian with respect to x is equal to 0. And that's just Qx plus C plus A transpose U is equal to 0. Complementary slackness There's nothing, because there's no inequality constraints. And primal and dual feasibility, well, there is no dual feasibility because there's no inequality constraints. And primal feasibility is just AX equals 0. So the KKT conditions are really just these two things that I'm underlining. Right, just these two conditions. And we can write them together into one linear system. Right? I can write them like this. Q times A transpose times A times 0 times X U must be equal to negative C 0. So that's just combining those two linear systems into one big linear system. Right? This says Q times X plus A transpose times U must be equal to negative C. That's from the first block. That's stationarity. And feasibility is just A times X plus 0 times U is equal to 0. So it's just AX equals 0. So this is one kind of mega system that we have to solve in order to get primal and dual solutions. Okay, again, maybe contrast to this one system we had to solve. That should have said negative C. Qx equals minus C in the unconstrained case. Okay, now it's an augmented system because we have to solve for a dual variable as well. This is sometimes called, you might hear this called the KKT matrix. That's just alluding to where this came from. Okay, so now you can solve quadratics subject to equality constraints. Okay, this example, I'll just go through this example so that we can practice the KKT conditions, but we're just going to quit after the KKT conditions. I don't want to go through the rest of the example. It's an example where it's somewhat interesting, but I think it's a more specialized problem, and it's an example where you can actually solve for the solution from the KKT conditions in a somewhat non-trivial original problem. I mean, here we could as well. Obviously, this is a system we can solve for the solutions, plug this into our favorite programming language. This is an example where the KKT conditions also lead to a solution method. It's more non-trivial, and I think it's more specialized. So I'll just I'll do the KKT conditions as practice, and then you can look at Boyd and Vandenberg, page 245, if you want to see how this leads to a solution. Okay, so the problem is something like we want to maximize communication across a bunch of channels, okay, subject to some budget that we're going to distribute to one of n to each of n channels. So x is like our variable for how much we're budgeting to a bunch of channels. It has to satisfy non-negativity and has to sum to 1. And you can think about log of some constant alpha I plus xi as the communication rate of the ith channel, where alpha I is some prefixed constant. So minimizing the negative sum of logs is like maximizing the communication amongst a bunch of channels. So just as practice, we're just going to look at the KKT conditions, and then I'll say you can refer to that chapter in Boyd and Vandenberg if you want to see how this leads to a solution. So the Lagrangian is just given by the criterion, say minus ui xi, right? I'm going to assign an inequality, a dual variable to every one of these inequality constraints, and I'll write these as minus x being less than or equal to 0. And I just have one equality constraint, and so I have one additional dual variable v that's, doesn't matter what sign I choose, but I'll just match the slides. Looks like I chose this. Okay, it's just this is my equality constraint. This must be equal to 0. That's my L function. in the notation from before. So the KKT conditions now, okay, if we look at stationarity, again, this is convex in x. Right, log is concave, so minus log is convex. So stationarity says that 0 has to be equal to the gradient of the Lagrangian with respect to x. And that is going to be equal to, okay, let's derive maybe a separate condition for every I. So we'll get for I equals 1 through n, the following condition must hold. The derivative of this with respect to xi is 1 over alpha I plus xi, the negative, minus ui plus vi. Right, because this is like the sum of the x's. If I differentiate with respect to xi, I just get 1. So that's stationarity, this condition. Complementary slackness. Well, we have these inequality constraints, and so what we know has to be true is that ui times xi has to be equal to 0 for all I. Right, so either our dual variable has to be 0 or xi has to be equal to 0. And then feasibility is usually very easy. Just write down the constraints. X must be bigger than or equal to 0. Sum of the x's must be equal to 1. U must be bigger than or equal to 0. Okay, so this is our KKT system. And it turns out that if we were to manipulate this system, this can eventually actually lead to an algorithm for computing x star. And it's a fairly simple algorithm that's called it's named water filling, after just kind of like an informal or an intuitive view for what it's doing. Okay, so it's basically you can eliminate the dual variable u. This should not have said vi, by the way. That's just v, because we only have one dual variable. And then you get a system that only involves x and v, and it turns out that you can exactly optimize out over x as a function of v. Now you get a system that only involves v alone, and that's a univariate system. There's just one variable, and there's this simple kind of algorithm that you can use to find the v that satisfies that nonlinear system of equations. Okay, and now because we've optimized out over x as a function of v, this just gives us the solution directly. Okay, so for details, I'll say just take a look at that chapter of Boyd and Vandenberg. Let's see. Let's do the SVM's example, and then we'll take a break. So we've seen SVMs a number of times. You guys may be sick of them at this point, but we're going to at least look at them one more time with the KKT conditions. So I think the KKT conditions for the SVM problem are actually very neat, and they explain a lot about what's going on in terms of the support points. So let's go through this as good practice, and also to see that deriving the KKT conditions for SVMs. Okay, so here's my SVM problem, classification problem. Okay, there's my SVM problem, and we'll do the same steps as we've been doing. We're going to form a Lagrangian, and it looks like I called V. Looks like I called V I the dual variables for these inequality constraints, and wi, the dual variables for these equality constraints. V and W. And it's given by, okay, taking the criterion, subtracting off the sum of Vi psi I, right? Because I have these being bigger than or equal to 0, I'll write that as minus these being smaller than or equal to 0 multiplied by the dual variables added up, and plus the sum of wi's times the function that I have less than or equal to 0, and that function is 1 minus psi I minus yi times xi transpose beta plus beta naught. So that's my Lagrangian. And now we're going to go forward and derive the KKT conditions. So the stationarity condition, which we always start off with. Everything that we've been doing, I guess, thus far is smooth and convex. So they've all been reduced to setting gradients equal to 0. Now I actually have 3 primal variables. In block form, I have 3 primal variables. So I can think about actually differentiating with respect to each of them to get a different block of the stationarity condition. All right, so let's start with this beta block. So take the gradient with respect to beta, set it equal to 0. I'm going to get 0 equals this is just beta, right? There's nothing here involving beta. This is the only term that involves beta. And this is equal to minus the sum of wi times yi times xi. Okay, so that tells me that at the solution, beta is equal to the sum of wi times yi times xi. Okay, so that's kind of neat because that's actually a formulation for the main thing we care about in the primal, which is the slope that determines the hyperplane and a dual variable. So if you were to solve the dual, this is the equation you'd use to get back a primal solution, at least in terms of beta. So that's that block. And that's this middle piece right here. Beta is equal to sum of wi, yi, xi. And now we can also, let's say, take a gradient with respect to beta naught. Okay, and that's going to essentially tell us that 0 must be equal to just the sum of the wi's, right? Because nothing here involves beta 0 except for this last term, times yi, sorry. Beta 0 times yi times wi. Those are the only terms we have. So this is going to be a constraint on our dual variable w. And lastly, we can take a gradient with respect to the size, and we'll get something like this. C times the 1's vector, right? If I were to differentiate this in every component, I just get the 1's vector. Minus this I can think about as minus v transpose xi, so that's just v. And this is going to give me minus w, right? The sum of minus wi xi I is like minus w transpose xi, and differentiating with respect to psi gives me just w. Okay, so these in boxes are the 3 pieces from our stationarity condition that I wrote down on the slides. Okay, and primal and dual feasibility I won't write down because these are the primal constraints. Dual feasibility is just these v's have to be bigger than or equal to 0. And complementary slackness is the last one. Okay, complementary slackness here is actually sorry, all of these have to be bigger than or equal to 0. The w's and the v's, because they're all inequality constraints. And complementary slackness here for the SVM problem is actually quite important and interesting. Okay, complementary slackness is a pair of two conditions because we have two sets of inequality constraints. The first is that Vi times psi I must be equal to 0 for all I. Right? This is the dual variable corresponding to that inequality constraint. And the second one is that Wi times its corresponding inequality constraint function must also be equal to 0 for all I. And that is this thing. 1 minus xi minus yi times xi transpose beta plus beta naught. Okay, so I claim we can actually learn a lot now about SVMs from really complementary slackness and these conditions here. These relationships here that we've derived between the primal and the dual variables. Okay, the first thing that we can learn is what I already said, which is that this is a relationship between a primal solution and a dual solution right here. Beta is equal to the sum of Wi, yi, xi. So it's given by a linear combination of the signed rows of x. That's yi times xi. Where the weights are the dual variables. Okay. So what we say is actually that these rows of x, they support the solution because beta is a linear combination of them if the corresponding dual variable w is non-zero. If the corresponding dual variable wi is 0, then that x didn't matter. Right? It didn't matter its value. The solution does not depend on it. Okay, it's not a function of that particular point xi. So the support points we call, again, these are the data points for which wi is not 0. And from complementary slackness, okay, this can be not 0 only when this is equal to 0. Because if this were not equal to 0, complementary slackness would force wi to be equal to 0. So support points only occur, okay, when this whole term is exactly equal to 0. In other words, when the predicted value, right, that we get at the point xy out of our SVM, or this is really the signed predicted value, is 1 minus psi I. So we've called these points, okay, the points I for which this equality happens, the support points. And now we can actually read off of the other complementary slackness equation to kind of characterize two different types of support points. Okay, so if we have a particular support point, let's call it I, and actually this psi value is equal to 0, then yi times xi transpose beta plus beta naught is equal to 1. Okay, and remember that this SVM classifier, it determines a hyperplane. It's determined by a hyperplane, I should say. That is of the form x times x transpose beta plus beta naught is equal to 0. And if we look at parallel hyperplanes that are defined by, let's say, x transpose beta plus beta 0 is equal to minus 1, and x transpose beta plus beta 0 is equal to 1, then everything in between these two parallel hyperplanes is called the margin. And what we've just said is that there is one type of support point, let's say xi comma yi, that has this property. So when I were to look at xi transpose beta plus beta naught, it gives me exactly yi. So supposing yi was a positive here, it was like a positive example, positive label, it lies exactly on the edge of the margin. Okay, and that's one type of support point. And for these support points, okay, because psi I is 0, Vi can be anything. Vi is allowed to be anything because of this complementary slackness equation. And W now has to be between C at its very largest and 0 at its very smallest, because of the that was because of the dual feasibility. W has to be bigger than or equal to 0, and this says it has to be less than or equal to C. Okay, so For support points that lie in the margin, the dual variable can be anything between 0 and c. For some other support points, psi I can be non-zero. Okay, and for such examples where psi I is non-zero, let's suppose that this was the scheme. I had a bunch of positive examples over here, a bunch of negative examples over here. Psi I is 0 and yi being plus 1. Okay, that's like I have a positive example that's just right on the edge of the margin. When psi I is bigger than 0, let's say if it's small, but it's positive, it's on the wrong side of the margin. Okay, so it's actually into the margin. And remember, the SVMs try to explicitly minimize somehow how many times these happen. That's because this is costing us a positive psi I, and that's appearing in the criterion. If psi I was actually big enough, this could even be on the wrong side of the decision boundary, right? It could also be happening that this was another positive psi I that was just larger. It doesn't have to be even the correct side of the decision boundary. But in any case, these are non-zero values of psi I. And if we look back at complementary slackness, that actually forces Vi to be equal to 0, right? Because psi I is non-zero. And that actually forces W to be equal to C in that component. So the dual variable is maximal. It's largest at such support points. Okay, so I think this is actually quite a rich way of viewing SVMs. It comes right out of the KKT conditions that, first of all, to recap, the solution only depends on a small number of points, which we call support points. Those are points for which the dual variable is non-zero. Even among those points, we can actually separate that amount into two camps. One is things that exactly lie on the edge of the margin. These are examples that are properly classified, that are just kind of as close to the margin as they can be. And the other are examples that are either improperly classified, like here. This could be a positive example. Or they're properly classified, like here, but they're just on the wrong side of the margin. And for those, actually, the dual variable has maximal weight. And this, there's a lot of uses for this kind of understanding of SVMs. One is a more recent development, which you're going to be looking on your homework question 3, is that playing with the KKT conditions like this actually can lead to an algorithm for screening away data before you run the SVMs, such that you don't change the solution. And that's because if you were to, let's say ahead of time, know that a bunch of the samples, xi, yi, would not have had positive dual variables, you could get rid of them. And it wouldn't have changed the solution based on this understanding we've developed, right? Because the dual variable would have been 0. They weren't support points. We didn't need them. And so if you're running SVM on a huge problem with, like, say, tens of millions or hundreds of millions of samples, if you could screen away a lot of samples ahead of time before you run the SVM, that could really save you a lot of computation. And that's something called screening rules, which you're going to be looking at on your homework. It comes out of directly KKT condition argument like this one. Okay, let's take a break. And when we get back, we'll finish with 2 applications of the KKT conditions. Okay, guys, let's now address constrained and Lagrange form, which is something that I think a lot of you would have seen frequently in classes or papers. Let's suppose that we have a problem that's of some constrained form. So we want to minimize some function f subject to an inequality constraint like h of x less than or equal to t. In terms of like a statistics or a machine learning application, think of this as a loss function, like this is perhaps least squares loss or logistic loss or something. And think of this as a regularizer, like this is the L1 norm or the L2 norm or some other regularizer. Okay, so this is a common form we encounter. And in some papers, people study this problem because maybe it's easier to study the constrained form. In other papers, let's say, with the same goal in mind, like the same idea that I want to regularize some loss function, we might actually do it in penalized form. And again, because perhaps for that application, it's actually easier to use a penalized form. And we also call this Lagrange form sometimes. And that problem looks like this: minimize f of x plus lambda times h of x, where lambda is a tuning parameter. Okay, and t is a tuning parameter in this problem as well. And it's often claimed, sometimes not even claimed, but just, it's implicit that these two are equivalent. That, we can think about somehow regularizing by constraints or regularizing by penalties. And we're going to ask now, is that true? Let's suppose that f and h were convex. Is it true to think of these as equivalent problem forms? And it's actually just an application of the KKT conditions and duality. So let's go from one to the other and then the other to the one. So let's start with the constrained form. So starting with this constrained form, which I'm calling C, if this problem is strictly feasible, right, if there is an x for which h of x is strictly less than t, then we know that strong duality holds. That's just Slater's condition. Right? This problem is convex by assumption. If it's strictly feasible, then that's Slater's condition will tell us that we get strong duality. And under strong duality, the KKT conditions must hold. Right? That was one direction that we saw today. They're necessary under strong duality. And what that means is that if we look at the KKT conditions for this problem, right, let's call the dual variable lambda for reasons that are going to make sense. Right, this is the Lagrangian. It's just f of x plus lambda times the inequality constraint that we're comparing to 0, h of x minus t. And stationarity in the KKT conditions says that whatever the solution was to our original constrained form problem, call it x star, it must minimize. Let's say it must solve this problem, minimize over all x, f of x plus lambda h of x minus t. Right? This means it must minimize the Lagrangian. That's just stationarity. Equivalently, it must solve this problem. Okay, it doesn't matter what t is, right? It does not. This is minimization over x. So what we've just shown is that if we had a solution in the constrained problem, and we had the constrained problem was strictly feasible, then there was some lambda for which that same thing solved the penalized problem. We just got that by invoking KKT stationarity, which means it's also a solution again in this problem for some value of lambda. Okay, that was the one direction. And going the other way around, well, if we have a solution to this problem, and we want to look at a solution, we want to claim that it's a solution to this problem. Okay. So this was C to L. Now we're going to go L to C. So to do that, we're going to just take x star, which is a solution in the Lagrange form problem. We're going to look at the KKT conditions for the constrained form problem. We're going to claim that they're satisfied, and therefore we must have a solution to the constrained form. And the KKT conditions are always sufficient, right? So if we can satisfy them, that's always going to imply optimality. So let's now look at the KKT conditions for the constrained form. Well, okay, we already saw this one, right? Whatever we're looking at, it must solve it must minimize the Lagrangian, okay, which we have by definition at x lambda, because that was what it meant to actually minimize the penalized criterion. So stationarity is fine as long as we take lambda to be the dual variable in the KKT conditions. Complementary slackness. Well, we must have lambda times h of x star minus t being equal to 0. So we haven't figured out what the t should be in the constrained form problem yet, but note this is satisfied by just taking t to be equal to h of x star. Right? If you said that you have a solution to the penalized problem, and you asked me what constrained form problem does that correspond to, I would just evaluate h at your solution and say that should be the bound t. Okay, that seems natural, and that's going to satisfy complementary slackness. And feasibility, well, by construction we have this. That was by a choice of t, and lambda was presumed to be non-negative. That's what we said to begin with, so that's satisfied as well. So we've just shown that if we had a penalized problem and we took the bound parameter t to be equal to h of x star, then the KKT conditions are satisfied, and therefore we know we have a solution in the constrained problem. These are the KKT conditions for the constrained problem. Okay, so what was the conclusion? We just showed that all solutions in L, no matter what value of lambda, are solutions in the constrained problem C for some value of t. Right? So the space of all solutions over all lambda is contained in all solutions over all t for the constrained problem. And we didn't get quite the exact perfectly symmetric statement, but we saw that for solutions in the constrained problem, for values of t such that that constrained problem is strictly feasible, they can be written as solutions in L. Right? If it wasn't strictly feasible, then we didn't know that strong duality holds, and we couldn't actually claim the KKT conditions were necessary. That's why we needed strict feasibility. So I'd say it's nearly a perfect equivalence. It's not exactly perfectly equivalent, but for most problems we care about, this actually is a perfect equivalence. And for most problems we care about, let's say h is non-negative. Like regularizers don't tend to be negative. If they're norms, for example, they're going to be non-negative. So if h is always non-negative, then the only value of t we have to worry about here is t is equal to 0. Right? Because let's just say h is a norm for simplicity. If you give me any value of t that's positive, I can always find a vector whose norm is smaller than that value of t strictly. It's not a concern, unless t was 0, in which case I would not have strict feasibility. But when t is 0, you can verify, or maybe you can just take it as a definition, the equivalence we'd get in the penalized problem is by taking lambda to be infinity. That's like going to be forcing the constraint to hold by taking lambda to infinity. So we still have an equivalence for that kind of border case t equals 0 by just allowing lambda to take infinite values. And then I'd say we do get a perfect equivalence, for example, in that case. Or more generally, let's say if h is non-negative, then they're completely equivalent. Okay, so this was just a basic proof of, I think, a common fact you would have heard about penalized and constrained forms. Okay, and the last thing I wanted to do, which I think we should have time for, I don't think it should take longer than what we have left, is give you cite a fact about uniqueness in L1 penalized problems, and then we're going to prove it too, just using the KKT conditions. And there's going to be a bit of maybe basic probability arguments as well, but I think those are not the main feature. The KKT conditions are. So here's the result. Suppose f is differentiable and it's strictly convex. So let's suppose f is just the least squares. It's just squared error loss. So as an example, we could take f to be 1/2 u y minus u squared for a response vector y. And so f of x beta is our familiar least squares criterion. Or we could take logistic loss, or we could take Poisson loss, or a bunch of other examples of a smooth, strictly convex loss function. And let me just emphasize, we're talking about strict convexity in the fit here, u, has nothing to do with whether or not it's strictly convex in beta. Okay, we're treating the loss at this time as a function of the fit, u. So this is always strictly convex. These are always strictly convex. They're not going to be strictly convex in beta, though, if x is, let's say, wide. But that's not what we're asking for. We're just asking for strict convexity in, not in the coefficients, but in the fit, in u. So let's suppose we're in such a setup. Let's suppose we have a feature matrix X. Okay, like it could be the features in this like regression setup. And it's n by p. No restrictions at all on whether n is bigger than p. P could be 10 million, n can be 10. And lambda is positive, anything positive. Let's consider the following L1 penalized problem. Minimize f of x beta plus lambda times the L1 norm of beta. So this covers stuff like the lasso, logistic lasso, any L1 penalized GLM. Okay. If the features have a continuous probability distribution, so if we think about drawing the entries of the feature matrix from any distribution, doesn't matter what it is, as long as that distribution has a density, so it can't be discrete distribution, it has to be continuous distribution, then with probability 1, there's a unique solution to this problem. And I think that's the punchline. The less maybe important or less surprising fact, perhaps, is that it has at most min NP non-zero components. So there's just one solution, and let's say if p was 1,000,000 and n was 10, it doesn't matter what lambda is. We're going to have at most 10 non-zeros in the lasso solution. So this property is called saturation of L1 regularization. You can't get more than min NP non-zeros in the solution. Okay. So this is, I think, to some might be kind of a surprising fact. To others, it may not be so surprising. I guess it depends on how familiar you are with L1 penalization. And it's an interesting example of where we get uniqueness without strict convexity. So this problem is certainly not strictly convex when p is larger than n, right? Because x is going to have a null space then that's non-trivial, so it's not going to be strictly convex. But we can still get a unique solution as long as the features are sufficiently random, if they have a continuous probability distribution. So let's go ahead and prove that from the KKT conditions. So the KKT conditions, you've seen these before, in fact, and because it's an unconstrained problem, they're just subgradient optimality. Right? There are no constraints, so this is just the subgradient optimality condition. That if I take a subgradient of my criterion with respect to beta, that criterion being f of x beta plus lambda times the L1 norm of beta, that this has to have 0 in it. That's all the KKT conditions say here. And this is, let's say, well, we know this is strictly, we know this is differentiable, excuse me. So its gradient is going to be its subgradient. And let's suppose we write S for a subgradient of the one norm evaluated at beta. Then this is what the stationarity condition says, or the KKT condition says. And I'm just rewriting that here as minus x transpose the gradient of f at x beta is equal to lambda, this should say times SI. And this is what it means for S to be a subgradient of the one norm evaluated at beta. It just must satisfy these conditions. It has to be the sign if beta is not equal to 0, or anything between minus 1 and 1 if beta I is equal to 0. So there are a few basic but important observations we can make at this point. The first one is that at the solution, x beta must be unique by strict convexity. So beta itself doesn't need to be unique. That's what we're trying to prove. But by strict convexity of f as a function of the fit, x beta must be unique. Okay, I will let you guys think about how to check that since we're kind of running short on time. Just use the definition of strict convexity. Suppose you have two different fits, x beta 1 and x beta 2. Use the definition of strict convexity and look at, let's say, beta 1 plus beta 2 over 2 as a proposed new solution. And you'll see that if the fits weren't the same, then you'd get a strictly smaller criterion. So the fit must be unique, and the KKT conditions therefore tell us that S itself is unique. The subgradient of beta at the solution is unique itself because, look, they only depend on x beta. So the left-hand side is unique. The right-hand side must also be unique then. Doesn't matter which beta we take. It'll generate the same subgradient. So that means we can define this unique set, which we call the equicorrelation set for L1 penalized problems, which is just the set of all let's say, feature indices, j, such that we actually get that SI to be equal to 1 in absolute value. In other words, it's the set of all j for which the inner product between xj and the gradient in absolute value is equal to lambda. So this is called the equicorrelation set because that means each of the features is equally correlated with the gradient, and it's also the biggest correlation possible in absolute value, okay, which is lambda. So this only depends on the fit, let's say. It's a unique object. And it also has this nice property that if we looked outside of S, then any solution for an I that's not in S must have a 0 at the component beta I. Why is that? Well, if we look at I that's not in S, then that means that one of these S's had to be strictly between -1 and 1, right? Because the inner product of x, let's say I, with the gradient was strictly less than lambda. So for that to be equal to lambda times s, that s had to be between -1 and 1. And if that was true, then beta I must have been equal to 0, no matter the solution, right? Because if beta I was not equal to 0, then the s's are forced to be plus or minus 1. So in other words, think about there's some big set S. It's uniquely defined in terms of the fit, and it contains the supports of all of the solutions. If you're outside of S, any solution has to place a 0 at that component. It's called the equicorrelation set. Okay, so we're going to actually prove that the features that are in the set S. So if we take a submatrix of the full feature matrix X and we only look at the features that are in the columns that correspond to this set S, I mean extract the columns numbered by S with this, they have to be linearly independent. We're going to prove that right now. Okay, and then we're going to see that linear independence actually is going to imply uniqueness. So this is pretty interpretable. This is saying that something like the lasso or logistic lasso or any of these L1 penalized estimators, they would never choose redundant features, right? They would never choose to bring features that are linearly dependent both into the active set. That would be kind of pointless. And this is a mathematical statement we're going to prove that's true about these types of estimators. So let's assume that actually they were not linearly independent. So the rank of this submatrix of the feature matrix was less than the number of things in it. Strictly less than the size of S. So they're linearly dependent, and we're going to try to come to a contradiction that's going to have to involve some kind of probability type argument. Because the statement we're trying to prove has to do with something to do with the distribution of the features. So if the submatrix of features was linearly dependent, then I could find one feature that I could write exactly as a linear combination of the rest. Right? Xi could be written as a sum of, say, Cj, Xj for all j that are in S but not equal to I. And I can just multiply both sides. I'm sorry, this is a bit of a typo. I just missed the Si on the right-hand side. I can multiply both sides by Si. Okay, and I can also multiply by Sj twice, right? Sj is a sign, And for everything in the equicorrelation set, it's equal to plus or minus 1. So I can multiply by it twice. That's equal to 1. So multiply by Sj twice. Okay, so I'm saying that the signed feature xi is equal to some linear combination of the signed other features, where these are the weights. These weights, let's call these aj. So it's equal to some linear combination aj times xj, sj. And if I take an inner product of both sides with a negative gradient, and I invoke the KKT conditions, everything here must be equal to lambda. That's why we signed it this way. All right, after taking an inner product with a negative gradient, the KKT condition says that every one of these has to achieve an inner product of lambda with a negative gradient. So I get lambda here, and I get lambda at every turn in the sum. And if I cancel the lambdas, assuming lambda is positive, I learn that these weights, aj, have to sum to 1. So I deduce that the sum of these weights must be equal to 1. Okay, that makes, in other words, what we said is that Si xi is equal to the sum of some, I should say, aj, sj, xj, where these aj sum to 1. That means that this is in the affine span. Si xi is in the affine span of these variables sj, xj. So a linear combination where the weights sum to 1 is called an affine combination. And it's easy to show that, this is the part I'm going to skip now because we're running out of time. If the entries of x have a density over R, then this can't happen. Okay, this kind of low-dimensional linear dependency can't happen. Here's a picture. Let's suppose I was 1. And I looked at the span of the affine span of x2, x3, x4. So those are the other things in S. Then they form a two-dimensional affine space, right? If I take the affine span of 3 vectors, generic vectors, they're going to give me a two-dimensional affine space. The probability that x1 lies exactly in that affine space is going to be 0 if it has a density. Okay, it's not going to lie in that affine space with any positive probability. So there's a formal argument that you can go to the reference at the end of this lecture to see the paper, but there's a formal argument that you can make to say that this never happens. It's probability 0 this happens. So essentially, if we have that the entries of x have a density, then we've just shown that we must have linearly independent things in the equicorrelation set. Okay, this can't happen. And there's a bunch of conclusions that we can make now from that. And the most important one is the uniqueness one. And that's gotten by now saying, let's restrict. Okay, let's actually partially optimize out over all of the components of the solution outside of S. That we already knew was 0, right? We knew that was 0 from the argument we previously made. So this is our kind of partially optimized problem over just beta S. And because this has linearly independent columns, this entire problem is actually strictly convex in beta S. Right? Because if we, for example, were to take we can take 2 derivatives to see that. But you can think about this now that xs has no null space. F is strictly convex. This entire term is strictly convex in beta S. So over just the equicorrelation set, the solution must be unique. And it must be 0 outside the equicorrelation set. Okay, and so that actually proves that we have a unique solution. All right. Thank you guys for staying a few minutes over. I just wanted to give that as an application of the KKT conditions. And I will see you guys on Wednesday.